Welcome to Mind Tier Learning, where we make GCSE learning and revision simple. In today's GCSE Maths lesson, we're learning how to represent inequalities. In the last lesson, we looked at solving inequalities algebraically. Today, we're going to take those solutions and show them visually on a number line. This is a really important GCSE skill because number lines help us understand whether values are included or excluded, and whether a solution goes in one direction forever or sits between two boundaries. Before we begin, remember to like this video, subscribe to Mind Tier Learning, and follow along carefully. By the end of this lesson, you should be able to represent inequalities on a number line using open and closed circles. You will be able to identify integer values that satisfy an inequality. You will learn how to solve and graph double inequalities, also called intervals. Finally, you will practice translating between graphical and algebraic notation. The key idea today is that inequalities describe a range of values, and number lines help us see that range clearly. Let's begin with the key vocabulary. A boundary is the start or end point of an inequality. On a number line, it is usually shown with a circle. An integer is a whole number. Integers can be positive, negative, or zero. An interval is the space between 2 points. In inequalities, it means a range of values. For example, if x is between 2 and 6, then the interval is the range of values from 2 to 6. Before we draw inequalities, we need to be able to solve them. Solving an inequality is very similar to solving an equation. We use inverse operations to isolate x. But there is one vital rule. If you multiply or divide by a negative number, you must flip the inequality sign. For example, negative 2x is less than 10. To solve it, we divide both sides by negative 2. Because we divide by a negative, the sign flips, so x is greater than negative 5. Let's start with a knowledge check. Question 1. Solve 3x plus 4 is less than or equal to 19. Question 2. Solve 10 minus 2x is less than 4. Question 3. Solve x over 2 plus 1 is greater than 5. Pause the video and try all three before checking the answers. Be especially careful on question 2 because it involves dividing by a negative number. Let's check the answers. For question 1, 3x plus 4 is less than or equal to 19. Subtract 4 from both sides. 3x is less than or equal to 15. Divide by 3. So x is less than or equal to 5. For question 2, 10 minus 2, x is less than 4. Subtract 10 from both sides. Negative 2, x is less than negative 6. Now divide by negative 2. Because we divide by a negative, the inequality sign flips. So x is greater than 3. For question 3, x over 2 plus 1 is greater than 5. Subtract 1 from both sides. X over 2 is greater than 4. Multiply by 2, so x is greater than 8. Now let's look at the visual language of inequalities. On a number line, we use circles to show whether the boundary value is included. An open circle is used for less than or greater than. That means the boundary number is not included. A closed circle is used for less than or equal to or greater than or equal to. That means the boundary number is included. A helpful rule is this. If the inequality symbol has an equal to line underneath it, fill the circle in. Let's represent the inequality x is less than negative 2. First, draw a number line and make sure negative 2 is clearly marked. Next, place an open circle at negative 2. We use an open circle because the inequality is strictly less than. That means -2 itself is not included. Finally, draw an arrow pointing left. Values smaller than -2 are to the left on the number line. So x less than -2 is shown with an open circle at -2 and an arrow going left. Now let's go the other way. Which inequality is represented by a closed circle at 5 with an arrow pointing to the right? Is it x is less than 5, x is greater than 5, x is less than or equal to 5, x is greater than or equal to 5? Pause the video and think carefully. The closed circle tells us whether 5 is included, and the arrow tells us which direction the values go. The correct answer is x is greater than or equal to 5. The circle is closed, so 5 is included. The arrow points to the right, so the values are greater than 5. Together, that means x is greater than or equal to 5. If the circle had been open, the answer would have been x is greater than 5. Sometimes questions ask us to list the integer values that satisfy an inequality. Remember, integers are whole numbers. Look at the inequality. -2 is less than x, and x is less than or equal to 3. This means x is bigger than -2, but can be equal to 3. We cannot include -2 because the symbol is strictly less than. But we can include 3 because the symbol is less than or equal to. So the integer values are -1, 0, 1, 2, and 3. Now let's look at double inequalities. A double inequality describes a range between two boundaries. For example, 5 is less than 2x minus 1, and 2x minus 1 is less than or equal to 11. To solve this, we do the same thing to all three parts of the inequality. First, add 1 to all three sections. That gives 6 is less than 2x, and 2x is less than or equal to 12. Then divide all three sections by 2. That gives 3 is less than x, and x is less than or equal to 6. So x is greater than 3, but less than or equal to 6. There are two main types of intervals. A finite interval has two boundaries. On a number line, it looks like a line segment or bar between two circles. For example, 1 is less than x is less than 5 would be a finite interval between 1 and 5. An infinite interval has one boundary and continues forever in one direction. For example, x is greater than 4 has one boundary at 4 and an arrow going right forever. Number lines help us see whether the solution is trapped between 2 points or continues without an endpoint. Let's apply the rules. If we have the inequality negative 3 is less than or equal to x and x is less than 2, what should the circle at -3 be? What should the circle at 2 be? And what integer values satisfy the inequality? Use the word bank to help you complete the sentence. Pause the video and try it before checking the answer. The completed answer is, if we have the inequality -3 is less than or equal to x, and x is less than 2, the circle at -3 should be closed, and the circle at 2 should be open. The integer values that satisfy this are -3, -2, -1, 0, and 1. We include -3 because the symbol says less than or equal to. We do not include 2 because the symbol is strictly less than. Now, let's think about a boundary problem. A student says Since x is greater than 4, the smallest integer x can be as 5. Is this always true? What if the inequality was x is greater than or equal to 4? How does the graph help us understand the difference? Pause the video and think about how the circle changes at the boundary. If x is greater than 4, then 4 is not included. On the graph, this would be shown with an open circle at 4. So if x must be an integer, the smallest possible integer is 5. But if x is greater than or equal to 4, then 4 is included. On the graph, this would be shown with a closed circle at 4. So in that case, the smallest integer is 4. The graph makes the boundary clear. An open circle means the gate is open and the boundary is excluded. A closed circle means the boundary is included. Instead of just seeing symbols, we can see where the solutions live on the number line. The key skill is knowing the difference between strict inequalities and inclusive inequalities. Strict inequalities use open circles. Inclusive inequalities use closed circles. Keep practicing this difference because it is one of the easiest places to lose marks in GCSE exams. You should now be able to draw inequalities on a number line, use open and closed circles, identify integer values, and solve double inequalities. Remember, open circles exclude the boundary, closed circles include the boundary, and arrows show the direction of the solution set. If this lesson helped, please like the video, subscribe to Mind Tier Learning, and watch the next GCSE Maths lesson to keep building your algebra confidence.